Okay. Had my camera disconnected and realized the thing I had plugged into the camera slot I can't unplug because it's currently processing video, so I had to go reach back and try and find an open USB port. Okay, let me pop open a couple things here, get chat up. Let's see. Okay, that's good. Need chat. Okie dokie. Okay, here we go. Okay, yeah, so it's already 3:32, so I guess I'll go ahead and get moving. I actually think I'm going to do one thing really quick. I just realized it's very warm in here, and if I don't open that window, I'm going to be swimming in my clothes. Go. Okay. Much better. Okay. So, yeah, I think I mentioned before that sort of these last lectures that we're going to be doing today and next week are sort of special topics, sort of things that aren't necessary for, for most of you probably doing your day-to-day stuff, but it's going to be some pretty potential useful stuff and may open doors that you didn't realize sort of were possible without seeing this kind of stuff. So today I'm going to introduce mapping and sort of geospatial data in R. It turns out R is actually a really good platform for working with geospatial data. It's a good alternative to using GIS software for a lot of tasks, especially geostatistical tasks. Next week, I'm going to go into working with model results and try and show you sort of like clever and easy ways to operate on model results that are probably easier than what you're going to learn in a lot of your CSSS classes, especially for making tables and predicted values from your models. Okay, so today's mapping. So what we're going to cover today is I'm going to show some basic mapping use of geospatial data in ggplot, like just using raw coordinates as X and Y variables in your aesthetics. I'm going to show you ggmap. Ggmap is a way to mash up maps from different sources into your ggplots, things like Google Maps and Stamen Maps. Used to do OpenStreetMaps, but not at the moment. That'll show you ggrepel for just sort of like a special task of repelling labels on things that might be overlapping on your plots, which applies to anything, not just geospatial data. And then we're going to transition over into advanced mapping. We're going to introduce, I'm going to introduce here simple features geometries, which are sort of the ISO standard for storing geospatial information used across most GIS platforms. And I'm going to show you some specific use cases with Tidy Census and Tigris packages to obtain Census Bureau data. I think I'm using ACS data in these particular examples. I don't remember if it's decennial or ACS. And then just sort of show you working with shapefiles and plotting all that stuff. It turns out it's shockingly easy to work with geospatial data in R and to make geospatial plots using shapefiles. Okay. So before I get started, I want to give you a quick plug here. So this book right here by Van Pabesma and Gomez Rubio's Applied Spatial Data Analysis with R is a classic in the world of programmatic mapping and geostatistics. This is one of those key books that is a really good thing to have on your shelf if you're going to get hard into spatial statistics, spatial data analysis. It is slightly dated at this point, though. It's about a 2013 book, and the authors, I think especially Edzer Pabesma here, are in the middle of producing sort of a new textbook in the vein of this, and like all good things in the R world, it is free and online. So if you click on the link through the slides, you'll see there's this new spatial data science with applications in R, which is an in-progress thing. You can see it was updated, 2 days ago on the current render here. It's just a big book down R markdown document. But it's got a lot of very detailed information on how to do just about everything you could want to do with spatial data. So including things like how do I do advanced plotting with like satellite and raster data? How do I work with, geometries and shapefiles? How do I make interactive plots and things like that? How do I do statistical models on geospatial data? All that stuff, kind of a one-stop shop. It's a pretty new book here. Yeah, if you want a textbook, my recommendation is this one is probably the best one in print that I'm aware of. But I'm not an expert in this area. I'm kind of a hedge geostatistician where I kind of learn things here and there and apply it in my own work. Another thing to consider would be the amazing John Wakefield CSSS508 Statistical Methods for Spatial Data. I love John Wakefield. I think he's one of the most entertaining professors in statistics, and he's very good, and he's a world-renowned expert on spatial statistics. It can be a challenging course, though. It's probably the second hardest CSSS class I took here at UW, behind the original Bayesian stats class, which is no longer taught anymore, which was deeply traumatic. 554 wasn't so bad, but it still was a lot of work. But so it goes. Yeah, it does have a focus a little bit more on statistics than mapping. So if you're more interested in mapping, you might look elsewhere. But if you want really to know geostatistics from somebody who's an expert, that's a great place to go. Another thing is if you want to use GIS software, specific purpose built software for it, like QGIS and ArcGIS, CSDE offers workshops on both of these platforms. I recommend QGIS because it's free software, so you don't have to pay for anything. It has a big community, it has extensive feature sets, and the professional geography people who I know typically use QGIS unless they're at like a major company or something that springs for a full ARC license, and then they're just using it because everybody else uses it there. QGIS can do pretty much everything the ARC platform can do, though sometimes it can be slightly unstable. I think it's pretty good. Okay. Yeah, so let's get into basic mapping here. This is just using ggplot and ggmap to do a little bit of mapping. Okay, so back in week 5, if you remember, when we were toying around with factors and stuff like that, we used a data set of 1 day of Seattle Police Department, like 911 calls, police incidents from 1 day back in, I don't even know what year it was, 2013 or something like that. We can load those up, and it turns out they have latitude and longitude in them. Well, if we got latitude and longitude, it's spatial data, and we can do spatial stuff with it. Okay, so let's take a look at these data again. You've seen them before, but to jog your memory. So here we've got 706 rows, 706 individual incidents the police responded to on this particular day, which appears to be 2016, sorry, not 2013, so March 25th, 2016. And we have a bunch of info on specific types of incidents they responded to, like car prowls and thefts and trespassing and all that. But importantly for our purposes, they have longitude and latitude, and they appear to be pretty precise down here. So it's hard to say exactly what sort of rounding they've done here, but most police departments record things to like street corners or midpoints between intersections. That's usually about as granular as they get. Some police departments like Chicago will do it only down to the block level, at least on what they release to you. So, if you ever work with police data, ask me about it. Anyway, so we got some geospatial information here, and we can do some stuff with it. Okay, so first thing, well, latitude and longitude are numbers. Anything that is a number can be given to ggplot as an X and Y value and made into a plot. So if you're working with geospatial data where you don't care about plotting over some sort of reference of some kind, you don't want to plot over a map, or maybe it doesn't actually reflect real world sort of values, you can just huck it right into ggplot and you're going to get a map. So here I say, ggplot, take my SPD raw data, AES, X is longitude, Y is latitude, throw a geom point on there. Chord fixed is a useful thing to put on some types of plots. What chord fixed does is make it so on the plot you can see here, there's an equal distance between a 1-point unit on this axis and a 1-point unit on this axis. So it forces it to be a kind of a square in its scale. This isn't perfect for latitude and longitude because right, the distance between longitude changes by your latitude sort of thing. So it can cause some distortion if you work with big units. But in this Seattle example, it's not too badly distorted, so it seemed fine to me here. Okay. Yeah, so you can see here these police incident data. You can see, if you know what Seattle looks like from the air, you can tell it's a sort of a crappy picture of Seattle, right? So you can see that the water kind of goes like this over here. Water zips here into Elliott Bay. You got kind of like Alki, West Seattle over here. You've got the south and southern border of the city here, and then you've got kind of Lake Washington over here, right? Okay, so you can kind of see Seattle in this. But if you were trying to show somebody else this map or do anything with it, this is not going to be very useful for them if they don't know what Seattle looks like, right? It's just like, I don't know what this means. I just see a cluster of stuff here. Who knows what that is? Okay, so we might want to plot this on top of some existing map as a point of reference. Okay, so one way to do that is with the ggmap package. So ggmap is a package that works with ggplot to allow you to plot your spatial data directly on map images it downloads from Google Maps or Stamen Maps. Stamen Maps, which you probably don't know about, is good for sort of artistic looking maps, certain minimal options, sort of nice looking things you can insert into something that don't just look like they're pulled straight from Google Maps. So what this package does pretty abstractly is it queries a server, say the Google Maps server, for a map based on the location you choose and the scale you want. You provide sort of like a zoom level, some latitude and longitude, okay? It then plots the bitmap of the image, that is sort of like the JPEG image or whatever in the background, which we call a raster image, as a ggplot object. So basically makes a background to your plot that you're doing that is a rip of an image from Google Maps. Then you can add more ggplot layers to it, things like points, density plots, text annotations, anything you can do with ggplot can be added onto that layer. It also has in ggmap some additional functions for interacting with Google Maps. Things like maybe you want to know the distance between different points in your data set by bicycle or walking, how long or how far those are, things like that. It also has some geocoding features, but it's not what I would recommend for geocoding. I'd recommend Tidy Geocoder, I think, is the one. Yeah. So a disadvantage to ggmap is that it's heavily reliant on Google Maps for a lot of operations. And Google Maps requires an API key if you want to use their services. And getting an API key from Google requires giving them your credit card number. Okay? So this is a little bit annoying. You just give it to them, but you can make a lot of queries. I mean, thousands of queries a day. So most people are not going to end up getting charged any money. But if you do like a lot of geocoding, it can add up. Okay? And the API key's I'd say main annoyance to getting the API key is actually that it's just the API key for general Google services, not just maps, which means you get spammed with emails from Google about every imaginable Google service continuously, which can be a little bit annoying. So here's a great question, chat. Does ggmap automatically make sure they're in the CRS? This is an excellent question from somebody who knows a little bit about geospatial data. The answer is no. So this is one of the disadvantages with ggmap is ggmap is spitting stuff out. Technically speaking, it's just sort of spitting stuff out in, I think it's just coming in WGS84. It's just latitude and longitude, but it's not really easily transferable to things that actually have proper geospatial identifiers. It's basically working everything as raw latitude and longitude units. It's great if all of your data are in latitude and longitude, you can convert it to it, plot it, and treat them just as numeric data, but you can't adjust the CRS to these on these Google Maps images without grossly distorting them, because Google Maps only returns images in their native sort of image format. So you can't really do any conversions, which sucks if you have your data in anything else, or if you don't want it projected the same way Google Maps pops out when you look at stuff. It's kind of annoying. Yeah, if you have real spatial data and real spatial data experience, ggmap is probably not the package to get base layers with. Yeah, but for the purposes of rather simple operations, it can be really useful. Okay, I'll get into coordinate reference systems and stuff here in the second half of the lecture today. Okay, so ggmap, it's like any other package. In R, you can do installed packages, ggmap, and get it. The thing is because it relies on making requests from a company's sort of online services, When companies change the way their API, their application programming interface works, that is the way your computer talks to their services, it breaks packages. And the author of ggmap doesn't necessarily update this thing super often, and that's because, you know, they're not getting paid to do it. In fact, it hasn't been updated very seriously in a little while, and I don't know if it's gonna get kind of deprecated or something. But sometimes you need to download a development version of it from GitHub. If you ever needed to download the development version of a package from an author's GitHub, you do it like this. You need the remotes package. The remotes package contains the function install GitHub, and then you'd give the username of the GitHub user and then the name of the repository on GitHub, and it will install the package on your computer just as if you'd done install.packages. Very often I like to work with the cutting edge versions of packages. And so I have a lot of packages I basically always do GitHub installs from. One of the ones that I always do this for is Lavon, the structural equation modeling software. Other things, you don't really got to worry about it too much. And this can be risky because sometimes they can be a little bit buggy, but you can always go get the one off of CRAN too. Okay. If you do this though with install GitHub, it might require compilation. If you haven't installed a compiler on your computer or activated a compiler if you're on a Mac, you're going to get errors. So there's a link on the main course website for how to enable compilation in R. I recommend doing it generally, but I don't cover it in the class. Okay, so if you got it installed, library ggmap will load it up. Okay, so the first function to know in ggmap is qmplot, which stands for quick map plot. So the idea with quick map plot is you say qmplot, you give it a data frame like SPD raw, give it an X of longitude data, a Y of latitude data, and it will just make you a map. So what this will do is it will automatically go and query an online service, download a map from it by default. Like in this example here, this actually looks to me, this doesn't look like a Google map to me. This looks to me like this might be a Stamen map or something. I'm not sure what the default is here. Anyway, it downloads a map image and plots your data on top of it. That is how easy it is to do. You just need a longitude, a latitude, and you can do things like here I manually set the color of the dots. The I here says I don't want to map it to a variable. Instead, what I want to do is I want to set it to a fixed value. This is just the dumb syntax in this particular function to do it. Same thing here, I had to manually set it to be partially transparent. Okay, so all I did is I provided a latitude and longitude. Notice I didn't say where I want my map to be, anything like that. I didn't tell it how zoomed in I want it. It figured all that out from the latitude and the longitude of the points. It kind of constructed what we call a bounding box, which is the square around your sort of data points and everything you want to see. It downloaded the image and it plotted my data on top of it. This is all the same incident data we had a few slides ago, but now we can actually see where everything is, and you can tell by the location of the points that it correctly got the latitude and longitude data. You can see because all the points here in downtown, none of them are stick out into the water. Same thing with Lake Union, Lake Washington, right? It figured out, it seems to be doing its job. Okay, so this is pretty damn easy, right? You just say, quick map plot, boom, get what I want. If you're working with like point data or something, ggmap is super easy to use. It's good for making really quick plots to go send to somebody, something like that. Just be like, there you go, a couple lines of code, and you've got yourself a map of some location. Okay. It's not super customizable, but you can do a lot with this. Okay, so underneath the hood of qmplot and also the qmap function, qmap sort of just provides a map without plugging any data on it. Beneath qmplot and qmap is a lower level function called getMap. What getMap does is it actually retrieves the base map layer that gets plotted underneath your ggplot geometry. Okay? So it has a few options which you could pass down from qmplot, or you could manually use getMap and give some options. First thing is it gives a location. If you use Google Maps, you can provide a search query. I could say Mary Gates Hall, University of Washington, and it will go zoom into Mary Gates Hall and return that. If you're using like Stamen map, you're going to need to give it a numeric vector of longitudes and latitudes for a bounding box or a point location. If you're using Google Maps, you can give it a zoom. The zoom levels are sort of these discrete levels. You can't give it decimal places. 3 is about continent level. 10 is about city. 21 is looking inside of a building for Google Maps. Some Google Maps has mapped the inside of a fairly large number of buildings, usually things like malls and some buildings on campus. If you had data from sensors or something you wanted to plot to a really small location, you could use size 21 or zoom 21. Okay. Now, there's a source option. Right now, I think the only functioning sources you can use in ggmap are Google to get Google Maps for general purpose maps and Stamen for more aesthetically pleasing maps. These Stamen maps are based on OpenStreetMaps, but you cannot currently use just raw OpenStreetMaps in ggmap because the OpenStreetMaps people decided they didn't want people to be able to sort of anonymously pull down OpenStreetMaps, and the author of this package hasn't enabled sort of an API key usage through the package, and I don't think he will. Okay. Anyway, next thing is for Google and Stamen maps, there's different map types that you can use. So for Google type maps, you can do terrain maps, terrain background, you can use satellite maps, hybrid maps, road maps. These are basically all the types of maps that if you open up Google Maps, look to a location and tab through the options, anything you can get by manually clicking that way, you can also pull down with map type. For Stamen, you have things like watercolor maps, toner, toner background, and toner light. I like toner light maps. It's a kind of a clean looking black and white map. Looks almost like architectural in nature. And you can also usually, but sometimes this is a broken feature, specify if the map should be in color or black and white. If you're if you're sending something to a journal, you often just want to do black and white because even if your article is never going to be actually in print, they still convert the damn thing to black and white and butcher it anyway, so you might as well just go ahead and do it for them. Okay. Yeah. So fair amount of options. Okay. So you could also add other layers other than like geom point to it. So here's an example of taking the same data I showed before, and instead of doing a scatter plot on it, I do a density plot. So here I'm going to say, let's generate a quick map plot, the same data equals SPD raw, the same longitude and latitude, but now I say here, geom equals blank. This says generate the quick map plot as a ggplot object, but don't plot my data in any way. Don't apply any geometry to it at all. So it's just blank. I then say here, my map type is toner light. This is not a toner light map, so apparently that was broken when I just rendered this a minute ago. Like I said, this thing can be a little finicky. And I said darken 0.5, which makes it 50% darker. Basically, if you did like darken 1, I think it would be black. Anyway, this darkens it so you can see light colored things a little bit easier. Now what I'm going to add to it is I'm going to add to it a density layer with my points. So I say plus stat density 2D, which is a geometry for adding densities that are two-dimensional in nature. I say AES, the fill of my density, that is the filled in polygons here that's going to generate, should be equal to stat level. Stat level is a special way to designate something in ggplot. This is essentially saying the stat function here takes an argument in here like level. What it's going to do is it's using the location of the points on the data. It's going to calculate a statistic, which is the approximate calculated density at every given point on this sort of thing. It's calculating the density for you using a kernel density algorithm. Okay? Don't need to know the detail about it, but know that the syntax is a little funky. If you need to do this yourself and figure it out, go online and look up like stat density 2D's documentation. Then I say, the geometry for this should be a polygon geometry, which is going to fill in polygons like this. Alpha 0.2 makes it partially transparent. Color equals NA makes no line drawn around the polygons. Scale fill gradient here just lets me say incident concentration. I set a title here, and then I set it to be the low concentration is white, mid is yellow, high is red. And that just sort of controls the way it ramps up the gradient. Okay. And now I have a little density plot over here. And due to the high concentration of the dots, we basically just see a massive spike right here in the middle of downtown Seattle, and everything else is just sort of some little globs in particular areas like the U District up here on Aurora, north of Green Lake, over here in Ballard, right? Which are the places you'd see more incidents. Okay. So Something you might want to do, throw a density plot. Density plots tend to be a little bit finicky because often you have really concentrated things. So you might have to take the logarithm of the density or something like that. You might have to tweak it a little bit. It's sort of a little bit of an art, and I'm not an expert in it, which is why this plot looks like this. Okay, don't use densities too often myself. Well, correction, I use densities a lot, but in the statistical sense rather than in the plotting sense. Okay. Questions on that so far? Stuff isn't too bad. It's a pretty simple package just for throwing some base layer maps. Okay. I'll keep moving on. There's no nodding heads today, so I never know if everyone's just taking a nap. Who knows what's going on? But that's okay. I'm good at talking to myself. So, okay. Okay. So, next I'll talk about is labeling points. Okay. So, let's go ahead and take the dots we plotted on a little bit earlier and add some labels to them. Okay. So what I'm going to do first here is, because we have a lot of points on that map I did earlier, I'm going to filter down to just downtown Seattle points. So what I did is I just eyeballed the latitude and longitude for what I consider the bounding box of downtown. I literally just went on Google Maps and clicked the sort of corners around the box, and I took the values straight off of Google Maps. So I'm saying that we're going to take our SPD raw data, and then I'm going to filter it so the latitude is greater than that and less than that, and the longitude is greater than that and less than that. So that kind of defines roughly a box around downtown. Okay. Latitude and longitude are numbers like anything else. You can just filter and use it like a number. Then what I'm going to do is make a data frame of just the assaults and robberies to sort of focus more narrowly on a class of crimes people might be more concerned with than most other things. Seattle doesn't have a lot of homicides, but it has a pretty good number of assaults and robberies. So that's one of the more serious crimes a person could reasonably expect to either experience themselves or know somebody who has. So I'm going to take the downtown data and then filter so that event clearance group is in either assaults or robberies. And then I'm going to rename event clearance description to assault label, which is going to give us a variable here that just is a label we can apply to the events. Yeah. So got some simple data. Now what I'm going to do is I'm going to say, take my quick map plot. My data is my downtown data. I just created my data are my downtown data. I should be careful about these things. Speak properly. Data are things. X is longitude. Y is latitude. My map type is toner light, or so I said. This looks like is this a color toner light map? It does kind of look like a toner light map zoomed in because I can see all the buildings and stuff. So I don't really know what's going on. Color, I just said fire brick red because for some reason this term I was into fire brick red. Alpha equals 0.5, which is about 50% transparent. The thing I'm adding here that's new is geom label. Geom label is not specific to geographical data or anything. You can use it on any plot you do. It draws labels wherever your data are. I say my data equals just my assaults data. Notice I'm using my downtown data that has all of my crimes, but I'm only using assaults down here. So that's why there's not a label on every single point in downtown. And then I say AES label equals my assault label. Size 2 makes these plates a particular size. If you increase the size, the plate and the text would be bigger. Make it smaller, the plate and the text would be smaller. So what geom label does is, like dead center underneath each one of these plates is, in this case, a data point associated with a strong arm robbery, an other assault, a strong arm robbery, other assault, strong arm robbery, and so on. And they seem to be a bunch down here. The thing about these labels, right, is they can just overlap each other. So we might not want them to overlap each other like this. We might instead want, where there's a whole bunch of points, we want these labels to push apart from each other so you can see everything there. Because for all we know, there's like 50 things right here, right? We don't know how many there are because they're all kind of covered up by overlapping, right? So geom label, though, itself, without using geom label repel, which I'm going to show you in a second, you can make it so all the labels are like offset in one direction or another uniformly. But what it doesn't do is automatically push them apart. So If we want to automatically push them apart, we can use the package ggrepel. So if you just do install.packages, ggrepel. ggrepel adds just some very simple functions to augment ggplot to enable your labels to not overlap each other. So all you got to do is do the exact same plot I just did, you know, downtown data, longitude, latitude, and so on. But instead of geom label, I say geom label repel. And the only other thing I change in here is I say segment.color equals black. The reason I do that is when the labels get pushed far enough away from the data points, it draws little lines to the specific observation in it, which is the segment. So segment.color black made those black lines so they're easier to see. So you can see none of the labels overlap each other. They're pushed away. Where they can sit directly on top of the data point, they do. Where they can't, they get pushed away. You could offset them so there's always a segment pointing over to it and then still make them repel. There's some flexibility too. So this is something you might want to do if you have like a lot of labels on something. It's kind of good to make it so they don't overlap each other. Okay. That is all I got for basic ggmap. Are there any questions on the stuff that I've covered so far? That stuff's pretty easy. Best way to kind of just play with it. Okay. So right now, all the dots are robberies, but the assaults are labeled. No, all the assaults and robberies are labeled here. So assaults are the strong arm robbery. Every single police incident in downtown is still shown. So basically all the dots you can see that don't have something pointing to them or label covering them are not robberies or assaults. The vast majority of crimes that the police are going to respond to, not crimes, but the vast majority of incidents police respond to are not going to be assaults or robberies. Robberies are fairly rare, fairly uncommon compared to the overall number of incidents.
Can we add multiple layers onto?
Oh, sorry, my audio's up. Shit, if anyone else is, okay, what was that?
Oh, I was just wondering, can we add multiple layers to a base map?
Yeah, you can do anything you could do to any ggplot. So you could start tacking stuff on top of it. You could throw some polygons, densities, all kinds of stuff. The thing is all QMplot and ggmap is doing is drawing a background. It's just adding a background to any ggplot.
Okay.
Yeah. So what used to be sort of the grid or whatever, it's just drawing over the grid. Yeah, which makes it very flexible.
Cool.
Well, not super flexible, I should say. It makes it flexible if you have latitude and longitude data. If you want to work in something other than latitude and longitude, it starts to get a little bit rough. In fact, if I'm not working in latitude and longitude, I don't use ggmap at all because it gets to be too awkward. There's other ways to get base layers in other projections, but the thing is if you want it in some kind of other projection, other units, you're not going to be able to get it from Google Maps or any of these other services because they don't produce them. Instead, you probably want to get a shapefile, which is where we're about to go. Okay. So the next thing to talk about is the actual fun stuff in this lecture. Let's talk about advanced mapping in R. That is doing GIS, Geographical Information Systems work in R using the SF package. Okay, so before I get into how to do these things, I have to give you a crash course in the terminology of geospatial data. If you know these terms, you'll be a lot better off searching for help and things like that. Geospatial data is sort of its own special world with a long history. You need to know a little bit of terminology to get some stuff in. So I'm going to talk to you about simple features geometries, coordinate reference systems, and shapefiles. Okay, so first thing. Up until recently in the R world, and when I say recently, I guess it's been a few 4 or 5 years now, the main way you worked with geospatial data was with this package called SP, the spatial package. Spatial SP was around for a really long time. I mean, it's the first last 20 years, 15 years or whatever. SP is a functional, powerful package that can do a lot of stuff. But SP does not store data the same way most GIS software packages do, like ArcGIS and QGIS. It can be a little bit bulky and complicated, and it definitely does not store data in something that looks to us like a tidy format. It can be kind of awkward to deal with. You have to do you might have to do list manipulation, weird operations directly on your data and stuff. It can be a little bit awkward. Okay. So the more recent SF package, which stands for simple features, implements the GIS standard ISO 9 something standard of simple features in R. And you click a link like this and you'll get some Wikipedia information on simple features. Okay, so neat thing about SF is, unlike the SP package, SF is well integrated into the tidyverse stuff that I show. It's not reliant on tidyverse. In fact, the SF people are primarily base R users, but it works equally well with base R and tidyverse stuff like I've taught in this class. For instance, it even comes with a geom for ggplot called geom-sf, which, as we'll see in a little bit, makes it ridiculously easy to plot geospatial data in ggplot. In fact, you'll be shocked how easy it is. You literally just say geom-sf and don't even give it any arguments, and it will plot your map for you. It's pretty crazy. Anyway, so it's well integrated into the tidyverse, making your life a lot easier. Okay, so this package is, and I say here, somewhat new. I guess it's solidly 5-6 years old now. It hasn't fully replaced the SP package, but it will fully replace it eventually. The principal authors of the SF package are the same people who wrote the SP package, and in fact, they're also the people who wrote that textbook I showed you at the beginning. They include Roger Byvand, Edzer Pabesma, and so on. But the SF package also has people like Hadley Wickham on it, who are tidyverse people and sort of big people in the R world. Okay, so package has a lot of people working on it. It's incredibly well maintained, constantly has new stuff added to it. It's very reliable and robust too. You rarely get any real bugs in it. Okay, so because SF is the new standard, I'm not going to cover anything in the SP package. In fact, I never use anything in the SP package anymore. We're just going to focus on SF. So you can do install.packages SF if you don't already have it, and then library SF will load it up. Okay, so let's talk about simple features. So a simple feature, a single simple feature, is one observation of data with some defined geospatial location. Okay. So simple features get stored in R in special data frames that have the class SF. So they'll be, if you do class on an SF data frame, it will say it is a data frame, but it is also an SF object. These data frames have two properties to them. The first property they have is they have a geometry. Geometries are properties which describe the location that that data point is in. It's usually a location on Earth, but it's not necessarily a location on Earth or even in the physical world. Okay? You can do things like network data that just sort of is like arbitrary locations of nodes and edges. You can do that in an SF data frame and store it that way. Okay? So geometries typically have 2 dimensions, but they can have up to 4. So you could also have, for instance, a height and a time dimension if you have data that goes, all over the place and across time. These geometries in an SF data frame get stored in a reserved list column. That name is usually geom. You can change the name of it if you want, but I generally recommend you leave it as geom. That column is a list. It is not a vector. Well, a list is a type of vector technically, but it is a list. It's of class SFC. List columns are something I have not introduced in this class because they're very advanced, but it turns out a data frame need not have its columns be a vector exactly. You could instead have a list of length equal to the number of rows in the data frame, but within each cell have an arbitrarily large number of elements within that cell on the table. This is actually very, very useful for geospatial data, because typically you'll have something like a polygon. If you imagine, for instance, if you imagine a square is defined by 4 points. If you were working with an SP data frame, typically to define those 4 points, you would need 4 rows of data where each row of data defines an X and Y location. So that's not too bad if you're working with squares. If you're working with the state of Washington and you want its outline, can you imagine how many vertices, how many little nodes are necessary to draw a nicely rendered outline of the state of Washington? It could be thousands of points. Do you want a data frame that has thousands and thousands of rows per state in your data? Probably not. The neat thing with doing a list column like this in SF is no matter how many vertices and edges and all kinds of things define your polygons, they only ever take up 1 row in your data frame. because that one cell in geom can contain hundreds of thousands of coordinates, but they're all stored nested into a single cell that you never have to look at. So the horrible things that lurk there can remain unseen. This is very nice. Okay? Another thing that this geometry column has is it has in its metadata a defined coordinate reference system. So the projection of the data, which I'm going to talk about in a little bit, is already stored in it. So you have this special data that tells R how to relate it to other things. Okay, so this is nice. The other property of an SF data frame is literally everything else, the attributes. The attributes of an SF data frame are every other column in the data frame which define characteristics of that particular location. So for instance, maybe if your data is state level data, the geometry might be the outline of that state, but an attribute might be the population of the state. So things like that are characteristics that define properties of the geographical area, but not the geographical area itself. So these are all the non-spatial measures that describe the feature. These are just standard data frame columns. You can have as many of them as you want. It looks like a normal data frame otherwise. So basically the idea with these SF data frames, they look just like everything you've been using all term long in the class, except they have one special geom column that you just don't touch. Leave it alone, let it do its thing, don't interact with it directly. It's a scary object. Okay, that's about it. So next thing I need to talk about coordinate reference systems. So a coordinate reference system, generally called a CRS, specifies what location, typically on Earth, the geometry coordinates in that geom column are relative to. So basically, what location describes 0, 0? If you think about it, we live on an oblate spheroid, so any particular location you pick is an arbitrary coordinate point relative to everything else. Picking a 0, 0 is arbitrary. Typically, you might use a 0, 0 of the intersection between like the prime meridian and the equator or something. I don't know. You can do whatever you want, but that's an arbitrary point. You could use anything as an arbitrary point. And it turns out there's a lot of arbitrary points that are used very commonly to define a coordinate reference system sort of starting point. The CRS also defines what one unit is. So what does it mean to go from a 0 to a 1? Going from a 0 to 1 could be 1 kilometer. It could be 1 inch. And so the CRS also defines how far that is. And then the CRS also defines one additional thing, which is the sphere that your data has been projected like on or off from. So you might be working with spherical data. You might be working with flat projected data, like a Mercator projection or something. These things are all contained in the CRS that's stored in the geom column. Yeah, so that's actually sort of the big problem with geospatial data is, well, we live on something vaguely spherical. Because we live on something vaguely spherical, no flat two-dimensional coordinate system actually accurately defines points. So you have to project that sphere into a flat plane. Your CRS does that job. But very often it's useful to work in the spherical data when doing certain operations and then move back and forth between spherical data and flat projected data. Okay, anyway. So the most common CRS you're probably going to encounter is WGS84. It's like World Geographic or Geologic Survey 1984. This is the standard for Google Earth. It's the standard for the Department of Defense, and it's what your GPS satellites typically talk to your phone in. Okay, so these are latitude and longitude coordinates. It's the most common standard you're going to see. If you have things that look like latitude and longitude, it's WGS84. Okay, typically. Yeah, so there's a couple different ways you can define a CRS in SF if you need to like manually set it. The way I generally recommend you do it is with EPSG codes. So EPSG codes are a numeric code which refer to some predefined coordinate reference system that's in their system already. For instance, if you want to use WGS84, its code is 4326. If you want to use Washington North NAD 83, it's 3689. If you work in geospatial data a lot, you'll end up memorizing the ones you constantly use and possibly even recognizing them on site when you see data in that projection, which is sort of the point that I'm at with a lot of these like Washington State ones. Okay, there's a million of these. If you want to know what your projection is, you can do st_CRS on your data. It will tell you the CRS it's in. ST transform will convert them, as I'll show in a little bit. Okay. One thing I'll say is I often like to work in 4326 WGS84 as sort of a uniform one, but I actually recommend not doing geospatial operations like unions, intersections, subtraction of features and stuff in 4326, because 4326 is not like, how should I put it? It's not projected in a way that makes your operations robust to like what would happen if in the real world you like subtracted features. You should instead project to some spherical some non-spherical thing, some proper 2D plane, like for instance, NAD 83 for the Washington state. Anyway, it'll give you a warning if you have your data in WGS 84 and you attempt to do like subtraction operations. It's going to be like, don't use this projection. Anyway, another way that you can specify them are proj 4 strings, or soon, I guess, proj 5 strings. These are text strings of parameters that define all the characteristics of a coordinate reference system. So for example, if you're working with NAD 83 and SRS 2007 Washington North, which is how I often get police data from SPD, the CRS for that is defined like this. It tells you some information on its projection. This is what Lambert conical or whatever. It tells you what latitude 1 signifies. Latitude 1, so a value of, I think, like 1 on my y-axis variable would signify a latitude of 48.73, a value, of like 2 is 47.5, 0 is 47. Same thing for like longitude. It has like an offset over here. It tells you the ellipse, the spherical ellipse it's using for its projection, how to convert to WGS 84, what units it's in, meters in this case, so on and so forth. Okay, so this sort of fully defines all the information about the projection to tell R and any other piece of geospatial software how to convert it to other projections. If you have a fully defined CRS like this, not just projection, but the coordinate reference system, R can, using these parameters, reverse engineer it essentially and let it convert to other things that also have these parameters. CRSs are nice because they give you all the information necessary to change it to some other CRS. Okay, so this is all complicated. You could easily have a class that spends weeks talking about this sort of thing. You just got in like 5 minutes, look up this stuff if you need to know how to do it. I generally, I'm not an expert in this. I mostly just have learned this stuff myself. If I really get into trouble, I go and email my friend Tim, who's used to be a surveyor and is like a big geospatial guy in social science. Anyway, so CRSs. Next sort of thing I want to talk about shapefiles. So geospatial data is usually stored in a shapefile, which stores geometric data as vectors with some associated attributes, which are the variables. Okay. Well, the thing about shapefiles is they're lying to you. They are not a single file. A shapefile is usually a bunch of different individual files. There's usually at least 3 of them when you download a shapefile, like you download it maybe as a zip file or something. It's usually at least 3 files in there. Typically, you're going to get a .shp file. The SHP is the actual feature geometries. That is the shapes of your observations in like geometrical terms. The next is a .shx, which is a shape positional index that just indexes all of those different observations and geometries. And then typically there will be a .dbf, which is a database file describing the features with additional data and things like that. That's just like an ancient data format. You could open up that DBF file and all sorts of other software. You could read it and pull stuff from it. Okay. If you are lucky, there will also be a .prj file, which defines the coordinate reference system, PRJ for projection. Okay. If you receive a shape file that you want to use and God forbid merge with other data you're working with, and they do not provide you a .prj, your mission has become figuring out what weird projection or CRS your data are in. If you're lucky, it's WGS 84, or sometimes you can figure it out depending on the source. For instance, if you get something from the city of Seattle, it's very often that Washington North one, right? I specified over here, NAD 83, one of the different NAD 83s. Okay, it's very often something like that. If that doesn't look right when you project it and say convert it back to latitude and longitude, you're going to have to go on a hunt. The nice thing is that the author of the Tidy Census package also made a package, which I forget the name of off the top of my head, which when you provide it with a coordinate with coordinates from a coordinate reference system you don't know, it will guess what the actual CRS is, and it's very accurate. I don't know what magic goes on behind the scenes there, but I've thrown weird stuff at it and it always guesses the correct CRS. So I don't know. Anyway, so you can tend to figure it out. Okay. So that's some lingo. Refer back to it if you need to know it, or look online for better sources on what I've provided, but that lingo is really useful. Okay, now let's talk about putting it into action and actually using the SF package. The lingo there is usually harder than actually doing it in R unless you want to do complex operations. Okay, so the SF package has a lot of handy functions in it. It's one of those massive packages where you don't memorize all the functions. Instead, you Google it, figure out what you want to do, and then eventually over time, you'll memorize a few common features or common functions. Okay, some useful ones you'll probably use if you work with spatial data are stread and stwrite. These are for reading in and writing out shape files, .shp files, and their assorted other files. There's a geom_sf, which is a ggplot geometry layer specifically for SF objects. If you have an SF data frame, geom_sf is what you're going to use for most of your plotting. ST as SF will convert a data frame into an SF object. You'll say like STSF, and then you'll specify the column that contains the geometry, and it will convert it to an SF object. stjoin joins data by spatial relationships. So you've seen left joins, inner joins, full joins, and all of that in dplyr. What if instead what you want is you want to join data geographically? So instead, maybe what you have is you have a bunch of polygons defining something like states in the US, maybe election precinct census tracts, and a whole bunch of point data. And what you want to know is which census tract, state, or whatever those points are in. To do that, you're going to use stjoin. And stjoin will use the geometry information in the two data frames you're joining and assign the things on the left side attributes from the thing on the right side that they are inside, overlap, intersect, whatever. There's a bunch of different options. The freaking awesome thing about geospatial data is geospatial data becomes a universal joining tool. If you have geospatial IDs on your data, you can join it to anything else with geospatial IDs. So if you get data sets that you normally have no IDs that identify them in any way, you know, got a bunch of crime incidents or something, well, if you got geospatial data on where those crimes happen, you can join them to property data, census data, police beat data, city transportation data, all that kind of stuff. It is a magical key to writing crazy new papers. So if you learn like geospatial data, basic geospatial joining, you can take all these data sets that people who don't have basic GIS skills don't even think that they can just huck two data sets together and spit it out. There's a lot of people who just live in this cottage industry of finding geospatially linked data sets, hucking them together and writing a paper. You can do a lot of cool stuff with geospatial analysis. I have like one project over the last 5 years without a geospatial component. It's just too useful. It's fantastic, right? Okay, good to know that. Next thing. Often you want to move between different coordinate reference systems, typically when you want to join data. Very often you'll have some data you got in one CRS and another data frame in another CRS, and you want to make the data frames kiss. And if you want that to happen, you need to transform one of them to be in the same CRS as the other one. So you can just say ST transform into the numeric CRS of the other data frame, or you could actually say ST transform and then inside ST underscore CRS the other data frame, and it will extract the CRS from that data frame and assign it to the other one. Okay. Yeah. Next one. So SF data frames are special. They are wonderful. But because they contain a funky list column, they get real angry when you do certain operations, including aggregations. If you aggregate data like running count or group by and summarize, it will often break on an SF data frame. If you want to do those things, you're either going to have to actually aggregate your geographical units in the process or remove them. Often you just want to join some data together and you don't care about the geographical information afterwards. ST drop geometry is basically how you delete the geometry column from an SF data frame. Because it's a special data type, you want to use ST drop geometry and not just unselect geometry. Okay. Other things that might be useful, ST-relate. Maybe you want to calculate, like, maybe you've got a bunch of census tracts and you need to calculate which census tracts border each census tract and get their neighbors. ST-relate can be used to calculate like neighborhood matrices and stuff like that for geostatistical operations. Another one that's good to know about, but I don't recommend using, is ST-interpolate AW for aerial weighted interpolation of polygons. Maybe you got something like you got polygons like census tracts, but what you want to assign to them maybe is you want to know how people voted in that census tract. Well, voting precincts like in Seattle do not have the same boundaries as census tracts. So if you want to assign voting data to a census tract or census tract data to a voting thing, you're going to have to figure out a way to reconcile these geometries. Aerial weighted interpolation basically proportionally assigns values from one geographical data set to another one based on how much they overlap. If you have two things that overlap 50% with each other, it assigns 50% of that one's 50% of that one's units to this thing over here. It's a complex mathematical operation that becomes trivial in R. It's one line of code and it will do it. I recommend, however, doing it using the aerial package, which is a superior way to do it. It's faster, better operations, better error messages, and better documentation. I use this all the time for aerial weighting stuff. Okay, good to know about. If you want to know more about it, email me or look it up. Okay, so let's do some fun stuff. So what we're going to do here, let's work with the voting data from traumatic homework number 5. You remember that voting data, or maybe you've blocked it out of your mind. Either way, that's perfectly fine. The thing is those data there are precinct level voting data from King County. Well, the thing about election precincts are they are a geographical area and they have shape files for them you can pull down from King County's GIS data portal. Okay, so you could download these voting precincts geographical data. Okay, so what we do, we could download this file. If you want to follow along, whatever, you could download the zip file directly from my website. Okay, what we want to do here, if you're a little clever with URLs, you could probably actually just pull it down directly from my website by replacing this period with the URL in the correct directory from my GitHub repo, but that'd be a bit involved. So what we're going to do here, let's say you got this shape file located on your drive. Notice what you do. You say stread and you provide it to the path of the .shp file. There will be other files in this same folder, but R knows that you point it to an SHP file, and then it goes and finds all the other files in that folder and grabs the appropriate ones like .prj files, .dbfs, all of that, because it figures them out from the .shp file. Okay. So question here, I've seen read SF before. I have no idea what read SF is. Is that in another read SF? I have no idea what that would be, because as long as I've always known, it's stread for SF. SF packages usually all st prefixes. You could Google and see what that's in, but I'm not familiar with it. It might be, I mean, honestly, it could even be an alias for this if it was like an older one, and it might do the same thing. Honestly, I'm curious. Yeah, I saw it right there. What is it? Oh, it's an alias. Yeah, okay, I was right. So read SF right there. Okay, so it's the exact same function. So it looks like read SF, same arguments, and yeah, it probably just calls on stread. Right? Nothing weird here. Yeah, they're aliases for stread. Okay, yeah, same function. Cool, didn't actually know about that. Okay, so anyway, we say stread, you give it a shape file, and then here what I did is I just selected down to 2 of the columns because there were a bunch of other columns in here I don't care about. All I cared about was the precinct, which was the name column, and geometry is not a column that exists in SHP, but is created by stread when it reads in the geometry from the shape file. Now, if you use stread, so it looks like that alias read SF, the difference between it and stread is it doesn't print all this output here. So if you use read SF, I guess it doesn't print all this text when reading in. It's quiet. Anyway, I like to read it in here because it gives me some useful info. So it says reading layer vote DST from this data source. It is a simple feature data collection with 2,592 features. If you remember that number from the homework, that's how many precincts are in King County. It has 5 fields. Its geometry is multi-polygon. It means the geometries in there can contain 1 or more polygons. Dimensions are XY. It's 2-dimensional. It doesn't have height data. Its bounding box here, its x-min is this number, y-min is this number. Those aren't that useful to us unless we know about NAD83 Harn as a CRS. Washington North, we know these units are in feet. Okay, so this is basically the minimum x is 1,220,179 feet off of whatever 00 is for NAD83 Washington North. Okay, useful to you? Probably not, but that's what all those numbers mean. Okay, I like to read things in here because often I'll read something in. If it doesn't have a PRJ file, it will tell me what its bounding box is. And I tell you what, you can tell latitude and longitude right away. So at least then you'll know to just assign WGS84 to it. If it's something else, you might be able to figure out based on, like, if you know it's a city, you probably can figure out if it's meters or feet and stuff like that. Okay, so we've read it in. Now I do your entire homework 5 in one line of code, well, one call of code. So what this is here is I read in the elections data. I filter it down to the US president and vice president race. I select only the data for the Seattle tracks. So string detect precinct Seattle gets that. I select only the precinct, counter type, sum of count, group by precinct, filter down counter type here to get only the presidential race, the number of registered voters, the times counted, only the 2 main candidates for president. I mutate a counter type. I just recode it. So Donald J. Trump and Mike Pence is just Trump. This is just Clinton. Registered voters doesn't have a space in it. Total votes doesn't have a space in it. I pivot the data out to counter type and sum of count. I calculate a % Democrat votes as the number of people who voted for Clinton in each precinct divided by the total votes, Trump divided by the total votes, and the turnout as the total votes divided by the registered voters. I select only the things I care about. I remove any values that have a missing value for PDEM. This is just removing all precincts that have no valid votes, basically. And then I join it to my precinct data. I say left join precinct shape because the precinct shape data's precinct identifier is named precinct. I don't have to specify it. They're both named precinct and they're the only common columns between them. If you have a non-spatial data frame, like all the stuff I just generated, and you join it to a spatial data frame, it does not inherit the spatial data frame, spatial data class from the one you join it to. As a result, you will then just have to say ST as SF. What this does is if the data frame that results from this join contains a column named geom or geometry, it will recognize it, extract the information to it, convert it to an SF object. Okay, so that's all I have to do if they have the same named identifier. This is now a precinct votes SF data frame containing a geometry and all of the data we had before in the homework 5. This is what that data frame looks like. If I glimpse at precinct votes SF, I get 960 rows. There were 960 precincts in the city of Seattle with valid vote totals. I look here and I see I have my precinct identifiers, which are all SEA stuff. I have my % Democratic vote, my % Republican vote, my % turnout, and this monster. This is the geometry column where the magic happens. Geometry here, notice its class. Its class is multi-polygon US survey foot. That is its class, which is a type of object, a type of column we have definitely never seen before in this class. It has a lot of information. This says here, each individual element of this vector, or technically each element of this list, which makes up the column, can have multiple polygons in it, and its units are US survey feet. Now, each individual observation of this, its entry here can be enormous. So right here, we see some polygon information. You see 1273698. That right there is one part of a 2-part coordinate. Over here would be another coordinate. For this particular precinct, depending on the shape of this precinct, there might be 500 of those coordinates sitting there in that single row. Okay, you don't want to look at it. It's probably massive. But the thing is, we don't care about it. It's not something we work with directly. We're not going to be doing math on these things. We don't need to access it. The fact that it's really complicated is hidden from us, and that's good because we never want to interact with it directly. What's nice is in this data frame, a single row of data is a single precinct, and that's all we care about and all we need to know. It's tidy data, despite the fact it's got some bizarre, hideous object lurking beneath the surface. Okay? That makes sense so far before I get into the fun stuff. Okay. There's a lot of these different geometry types too. You could have like single points, single polygons, all sorts of things. Multi-polygon is one of the most sort of like flexible ones. You can also have lines and stuff. Okay, anyway. So let's show you how easy it is to make a map. So what we say here is, I want to make a map of the % Democrat votes. I'm being visited by a cat. Come here. Come on. Oh, you want a meow from your box? Oh, you're such a great cat. I know. I'll feed you one day. Okay, so she's saying hi. She sits over there, but she doesn't want to come play. So what we got here, we can say here, I want to make a ggplot. I'm going to use my precinct votes SF data frame. I want to fill all of my precincts with the % Democratic vote. Okay, fill, of course, determines the color inside of something like a polygon on a ggplot. I then just say geom_sf. Size NA here just removes the outline around polygons, and then the rest is just aesthetics. Theme void removes the background and stuff, and then I added a legend at the bottom. And here is the % Democratic vote in every election precinct in Seattle that reported valid results. Okay, so all of the magic happened from geom_sf, and I didn't have to tell it anything about geometries. I don't give it an X and Y coordinate because it knows how to get them from the geometry column in the data set. You don't give it anything. Okay, this is magical, right? You can make maps with anything you have once it's in SF format, and you just say geom_sf, and it just spits it out. Okay, pretty neat, huh? It's super easy. Got any questions about this? We're gonna do some crazy stuff here in a bit, but that's how easy it is. I love SF. I make maps all the time because it's super easy to make maps. You gotta get the data in, get an SF format, clean it up and stuff. Once you got an SF format, just say ggplot, huck it in geom_sf, your work is done.
What would you do to layer this on top of another map of the region, for example?
Have a shapefile for that too. I'll show you here in a minute, automating downloading like census data and stuff like that. There's a lot of like packages you can use to like pull down data from other sources, but you just get some other shapefile and then stick it, do another geom_sf call with that shapefile. As long as they're in the same CRS, it just puts the second one on top of the first one.
Okay, cool.
In fact, I'm going to do that later too.
Thanks.
Anything else? We're going to do some fun stuff in a minute, but it's pretty straightforward. Okay, so let's keep moving. Okay, so the next thing I want to talk about the tidy census package. The tidy census package is one of my favorite little R packages. It's had some instability lately, not due to the programmers or anything, but because of shakeups at the Census Bureau where you can't download any of the damn data I want because their API endpoint got shut down for everything except like the most recent census. But anyway, this is still a fantastic package, especially if you're working with recent census data. So Tidy Census is a package that allows you to search, among other things, the American Community Survey and decennial census for variables. So it'd be DE, decennial, not I don't know. Anyway, and then you can download data from the census in ACS, but it also has like the current population survey, census micro data, a whole bunch of other stuff is in there too. You can download them and it automatically spits it out as tidy data frames. and not just tidy data frames that are SF format with the geographical boundaries of whatever thing you downloaded. Okay, so this takes care of all of the worst things about working with stuff like census data and geographical data, which is like manually downloading it from the website, grabbing a shapefile, join it to the shapefile. It automates the entire process. Okay, so yeah, this is one of those ones before I knew about this package and the stuff that did it, it was so laborious, and I got this, and honestly, it was so amazing. I couldn't even be upset about all the time I wasted before. Anyway, so the one thing about this is kind of like the Google ggmap and the Google API, this package utilizes the census API. So you need to obtain a census API key. So an API, as I sort of mentioned earlier, is an application program interface. An API is a computer interface that exists as a native method of communication between two computers. It's how two computers talk to each other to get things done. A very common way for that to happen is via the HTTP protocol, which is how your web browsers talk to websites. This normally uses the HTTR package in R to do this communication. If you need to make R talk to a website or a web server, you probably would use HTTR or something that interfaces with HTTR to make those calls. Okay, so R packages that talk to websites or online services basically always use an API to talk to them. If you work with Twitter data, Facebook data, any of that shit, it's going through their API. Okay, it's not like scraping it down from them. APIs are nice for everybody. APIs make accessing the data easy, but at the same time, they allow websites to control access to their material. So it makes everybody happier, makes it way easier to work with their stuff and way easier for them to control what you can do. Okay. A thing though is sometimes you want to get things that a company's API does not permit you to download, or they don't have an API. Craigslist is an example of that. In my department, we have this very large scale effort to get Craigslist rental data. Craigslist doesn't let you pull down data from it. In fact, they also ban your IP address if you scrape data from them. So the people in my department use an automated programming language that simulates being an actual user to the point of opening up browser windows, simulating clicks, answering CAPTCHAs and stuff to download Craigslist data to get rental listings and information, which it then parses into spreadsheets automatically. There are clever ways to bypass limitations that people encounter. So you can do that. Most of the time, though, you can use an API. So I said before that the Google API is annoying to sign up for and it requires a credit card. The exact opposite of the Google API is the Census API. The Google API, you go into this website for this massive multinational corporation, you jump through all these hoops, you sign things up, you give them a credit card. The Census API key, the website to give you one, looks like it's going to ask you for a credit card to steal it from you. I'm going to show you what is one of my favorite websites that exists out there for social scientists. It is how you request a Census API key. Before I click this, let me tell you, this is an official government website. That is how you request an API key for the census. You put in a name, which it doesn't check, an email address, which I'm not even confident it checks. You say, I agree to terms of service you don't have to read, and you press a button and it gives you an API key. It then is never checked and nothing else happens. This looks like the kind of thing that if you opened up in your email and you gave it any information, you would start receiving spam emails. It would steal your credit card or something. This is an official government website. I love it. It's one of my favorite things ever. Okay. So it takes nothing, absolutely nothing to get a Census API key. There's no reason not to do it and to use it. And I've never run into limitations, and I definitely abuse their API. Okay, so easy peasy. So once you got an API key from the census, what you got to do with Tidy Census, you do library Tidy Census. You have to install a Census API key. To do this, you just say Census API key and you give it as a string in quotes. You only got to do this once and then it installs it permanently into your R installation. You don't have to put it in scripts or anything. You got to do it once and then it's in there. Don't put it in scripts and stuff. it's a good habit to not give people your API keys to stuff. For the census, I don't think you can do any harm. But if you like give somebody your Twitter API key, they could post tweets on your timeline and stuff like that. Don't give people your API key. Anyway, next, useful functions. Load variables will load a searchable list of census variables from whatever data source you're after. So you might say something like year equals 2015, and that will be the end year, say, of 2015 ACS data, American Community Survey data. You can then say which data set you want. You can get the documentation for load variables to see your options. I'm actually kind of variable data sets in here are things like all these different ACS5, ACS3, and so on data sets. There's a few different things that are available here, but there's also other data in here, public use microdata series and things that are kind of useful. Okay, so that will load up variables. So the thing is if you've ever worked with the ACS or the census, those are really big data sets. So you don't load the entire data set. It takes a little while to even load the list of the variables. And then what you can do is use those string manipulation functions we learned the other week to browse that list, find the variables you want, get their variable ID names, and then give that to the get decennial or get ACS functions. Using these will actually go and download the census variables, and if you ask for it, they're geographical boundaries. Okay, so what you'll do is you'll provide to the variables argument a vector of the variable IDs you can get from load variables. You'll give it a geography, which are unit of analysis. You can do things like states, census tracts, blocks, block groups, MSAs, you name it, all sorts of different units. We're going to use a few today. You give it a year. It could be census years. It could be the end year of the ACS. So for ACS, you'd be like year would be the end year. Like 2015 would be the ACS 5 year from 2011 to 2015, so on. If you say geometry equals true, it will return an SF geometry with the data frame. It pops up as an SF data frame. Okay. So let's see this in action. Okay. So I say, let's load up the tidy census package. The first time you run it, would have to say census API key. You put your key here and install equals true, and then you never got to do it again. Okay. Now what I say here is, I want to look at all the variables in the 2015 end year ACS 5-year data set. So I say load variables, 2015, ACS 5. Then just as an example, I looked at the 10th through 18th row of this, so just 9 rows here. I print it to console. This is the kind of thing you're going to get. You're going to get a name, which is the variable ID that you would give to something like get decennial. You have a label on that variable like estimate total male 20 years in a concept sex by age. This variable, if you ask for it, the get decennial is going to spit out a column of data containing the estimated count of males who are 20 years old in that geometry. Okay, so that's how you do it. Basically what you want to do, if you didn't know the name of it here or something, you would use functions like string detect to filter this data frame down by label or concept until you can find the variables that you want. I find this easier than using the census online browsing tools. I just pull this whole thing down. I use a bunch of regular expressions and I hunt down what I want. Okay? Once you get good at regular expressions, you can find stuff so fast. Yeah, so that's how you do it. Yeah, and then if you use the same variables over and over again, you just end up memorizing certain codes, which is what's happened to me because, I study the same things over and over again. Okay, so what I'm going to do here now is, let's say I searched through and I found a couple of variables that I want. The variables that I wanted here were like the total population, count, and the total count of people responding as being any black. Any black would be, they respond being 100% black or mixed race, and one of those mixed race categories is black. Okay, so what I'm going to say here is I'm going to create a King County object. To do that, I'm going to assign to it the result of getting some ACS data. My geography is tract, so I'm getting tract level ACS data. For the state of Washington, specifically King County, I would like the geometry, so I'd like the boundaries of those census tracts. Then my variables are B02001_001E, which is the total count of population in that tract, and B200901, which is the total Black count population in that tract. Then I say I would like my data outputted in wide format. So as I've talked about in this class, there is long data and there's wide data. The thing is, in tidy census, wide data is actually what we typically think of as tidy data for our purposes. If you say output wide, what you're going to get from the ACS is this. You're going to get a geographical ID for the census tract. This here is a FIPS code for census tract 113. That is 53 is the state of Washington, 33 King County, 113 is census tract 113, which you can see census tract 113 King County, Washington. Then you notice I requested 2 variables, these 2, but I got 4. I got the one I actually requested, which is the count. Then I got this, which ends in M. This is the margin of error. The American Community Survey returns estimates, not exact counts like the census. So any variable you asked for also comes with a margin of error, so you can put bounds on your estimates and stuff. I typically don't actually care about that marginal estimate unless I'm doing something fairly advanced. If you say long format, it does not put these in separate columns, but instead has one column for the measure and another column for the values. And so they're all like in a super long format. I usually want wide format, so I say output wide. Then what I would normally do is discard the margins of error because I don't care about them. Notice it also returned a geometry column, which is multi-polygon in degree unit. By default, it returns things in latitude and longitude, and you can tell because -122.3551 sure as hell sounds like something on the West Coast to me. Okay, so what we have here is a spatial data frame containing a little bit of census data and some tract identifiers. And if you know anything about King County, you know there's 398 census tracts in it in the current census. Okay, well, not the 2020 census, there's more now. Anyway, 2010. So we got some data, let's do some stuff with it. So what I'm going to do here is I'm going to get rid of those margin of error columns. I'm going to rename the estimates and I'm going to mutate a percentage variable that I can plot. So I'm going to say overwrite my King County data with my King County data and then remove the columns that end in M. These are my margin of error columns, which I do not want. And then I rename this variable to be total population because that's what it actually is. And this variable to be any Black because that's actually what it is. So I know these IDs correspond to these measures, so I'm going to rename it something I can understand. And then I'm going to say, let's mutate a new any Black column as a percentage, which is going to be equal to anyone responding, any Black in the census, or the ACS rather, divided by the total population, which will yield a percentage, a very low percentage because this is a very white county. Right? So we see glimpse, King County. Now what I have is a very simple data frame, the GeoID, name of the census tract, and just the total population, percentage, any Black, which as you can see sometimes is hella low. There's like 1 person in this census tract, right? Okay, a few, but yeah. Everything else is the same. Very simple data frame. Let's do some stuff with it. Okay, so what I'm going to do is I'm going to make a plot of this. I'm going to say here, take my King County data, and then like I did earlier, ggplot AES fill equals my percent any Black for each census tract. And then geomsf, again, I don't like outlines around my geographical units, so I remove them by saying size of the line equals NA. Then I do a couple funky things. I say coord SF. Coord SF is a way to control the coordinates and projection and stuff of geomsf, anything you plot using geomsf. Here I say my CRS is projection, longitude, latitude, datum, WGS84. It's WGS84 data. Datum equals NA over here removes graticule lines and outline, or graticule lines. Graticule lines are things like the lines that cross all the way across the map to show you longitude and latitude. Datum NA is just the weird syntax to make those not show on the plot to make it a clean plot because I don't actually care about the exact longitude and latitude. I then say scale fill continuous, which is going to control how this variable appears on the map. I name it any black. I put a line break after it because it looked better to jump up the title a little bit of a space. My low is a particular kind of purpley color I like. My high is a different purpley color that I like. Theme minimal trims off most of the extraneous shit on the plot. And then I give it a ggplot proportion any black, and that's the title. Okay. This is my plot here. This is the percentage black in every census tract in King County, Washington. Okay, so if you know generally what King County looks like, and you got Puget Sound over here and stuff, you can kind of figure out where places are. What about this plot do you not like? What looks weird about this? Or at least unintuitive. It is floating, that's fine though. I know what King County looks like. I'm okay not having stuff bordering around it. What about the interior of this thing? Is King County's landmass fully like contiguous like this? What exists over here? Like, what is this right here? Why are these census tracts all funky and smooth looking right here?
Lake Washington.
That's like Washington. Okay, so if you showed somebody this, it would look like this is one big landmass or something like that, which is not accurate. And this is just because of the way census tracts are. Census tracts go all the way into landlocked water bodies. They follow ocean and things like that, but they actually go all the way into the middle of, say, like Lake Washington. Okay, I don't like that. I would like to fix this to make my plot look prettier. So instead of having the actual census tract boundaries, I'd like to remove all the water from this plot so that people can see Lake Washington. So I'm going to teach you some cool stuff on how to do that. So the idea here is we can download a different shape file that contains all the shapes of every water body, even quite small water bodies in King County. And then we can subtract the water from our prior geometries. So if you ever want to do this in the future, copy my code to do this and cite me or put a little thanks, because this function right here will do it for you without having to think about it. This is a function created here called sterase. I assigned to it, it's a function of x and y. The x is the geometry we want to subtract things from. The y is what we want to remove from x. And the way it works is complicated. I'm going to briefly explain it, but it's okay to not understand. In fact, I would highly expect that you don't understand what it is that's going on here. I sometimes barely understand what's going on here. I just know it works. So what we do here first, we take the thing we want to remove from x, and we take it and combine it into a single geometry, and then unify it into essentially one big multi-polygon. These things together take it, so normally every body of water we download would be its own little polygon, 10,000 objects or whatever in King County. Well, if you want to do a subtraction operation, the more things you subtract the objects on the right side, the longer it takes. Even though it's the same subtraction operation, it has to perform each one pairwise. So it's a lot better to subtract one thing once than 10,000 things one at a time. So what we're doing here is we're combining any number of bodies of water into one thing. Okay, well, if you do that, sometimes it's going to create errors in the geometry, self-intersections, all sorts of little problems. stMakeValid is a function that will validate the geometries and fix problems in them. It sort of just goes in and figures out how to, for the lack of a better word, unfuck the geometry so that they won't cause you deep problems. Okay. So stMakeValid. Then you say, I would like to take the difference of x and these fixed unified geometries. Okay, so you just give it x. If x already has problems, you might want to say stMakeValid on x and fix it first. But if you got to this point, it probably doesn't have any problems. Then what we're going to do is we're going to get all those bodies of water. To do that, we're going to use the Tigris package. If you've installed Tidy Census, you already have Tigris, because Tigris is where the shape files actually come from. The guy who, I think it's Kyle Walker, who created Tidy Census, also created Tigris. Tigris downloads the Tiger line files for the US sort of like geographical features. You then say, Tigris, use the area water function, I want bodies of water from the state of Washington and King County, and I want them to be in SF data format. We assign this to King County Water, and all I got to do is say, take my King County data I'm working with, and then erase all the water, which I assign to the object KC no water. Okay. Now I do the same plot. I change no code, except I use KC no water, and now it looks awesome, right? So the idea here is I've subtracted every minute body of water, right? All the little mountain lakes and everything right here are on it, the rivers, all of the lakes, everything like that. The streams, you can see Green Lake and you can see the Duwamish and everything, right? Every little body of water is here. And if you zoom this in, really, I mean, everything is there. Like it's got all these tiny little rivers and creeks and all kinds of stuff. Okay, so this is the exact same plot as before. It's the exact same data. The difference is people will much prefer to look at this one over the prior one. So if you're going to put it in a paper or something like that, subtract the water, people will think it looks hella cool. That is basically my recommendation. People love maps. Everybody loves maps. If you're going to give a talk somewhere, figure out some way to present your results with a map of their town or city or whatever, or their state. Right? If you're going to, if you do a paper, do a map. If anything is geospatial, people love maps. Stick a map in there. Whenever possible, put a map in there. Nobody ever complains about a map. Okay. So yeah, I recommend doing and dress them up a little bit. And with SF, it's pretty easy to dress them up. So I always do this kind of stuff. I always subtract the water just because I can, right? So you do it, now you got a pretty map. And also it's useful because people know where bodies of water are. So using them as a reference, if anybody knows the area, they know exactly like the shapes of coastlines and stuff. They can be like, oh, I used to live like right there and stuff like that, right? People like that. And once you anchor people to it, it gets people more engaged. Anyway, I like that kind of stuff. It's pretty neat. Okay, so that's neat. Let's do it again. So the nice thing about code like that is it's essentially completely recyclable. If you've downloaded data for one geometry with tidy census and plotted it like that, you can do the exact same thing again for any geometry you want. So what I'm doing here is I'm going to repeat the exact same plotting operation here, but I'm going to do it for the entire state of Illinois. Okay, so here I'm going to say get ACS data. I'm going to say tract level geography again. I'm just changing state Illinois, and I'm not specifying a county. I'm just saying, give me the entire state. Geometry true, same variable, same output, exact same operation. Everything else is copy pasted except that, right? I assign it to PB state. I don't remember what PB stands for here. Yeah, I don't remember why it was PB. Lead state. Anyway, so then what I'm going to do is the exact same plot code. This is the same plot code. I changed nothing. And now what do we get? We get Illinois, every single census tract in Illinois. And if you know anything about Illinois, Chicago got like 1,000 census tracts up here, right? Every single one of them is there, I assure you. And it's still plotted instantaneously, even with thousands of units on here, because SF is a pretty efficient package when it runs through ggplot. Okay. So I look at this plot here, and I know a little bit about Illinois because my dissertation entirely uses Chicago data. But I look over here and I look all over like Illinois and stuff. And you might look at something like this and be like, okay, it does look like the Black population of Illinois is highly concentrated in particular areas. And you might guess to yourself, well, I bet they're concentrated in urban areas due to, the result of things like the Great Migration and stuff like that if you're a demographer. But you might not be 100% sure about it. So something you might want to do is do something like, let's add the urban boundaries to this map to see if that's actually true. Some of these big census tracts look like maybe they should be rural because they're big like that. Let's see if that's actually the case. So let's augment this map. So what I'm going to do here is I'm going to add another layer using a second geomsf call. So there's sometimes a lot of reasons to do this. So let's say you plot in some geospatial data and you want to do anything like this. Maybe you've got like some polygon data, but then you want to add points. Maybe you want to do things like highlight the cities in some states. Maybe you want to put individual crimes in the police beats on your police data. Maybe you want to do things like add some lines. Like you've got a bunch of census tract data, but you also have the street grid for the city and you want to plot the street grid on top of it. And then maybe plot some points on top of that. Okay. If any of you all were at a CSDE talk this last Friday, you probably saw a map I made that used the street grid, point data, and census tracts on top of each other. Yeah, it was like 3 lines of SF code to do that, and it was a pretty map. It was just 3 geom_sf calls, 3 different shapefiles. Okay, so you might do something like that. You might also do things like add outlines or highlights, like elevation contours. You could go and grab topographical data and do contour lines on top of stuff. What I'm going to show here is I'm going to add urban boundaries to that prior map. Okay, so to do that, I'm going to use Tigris again, because Tigris is amazing and it does everything, so long as you're working with US data. If you're working outside the US, you got to find some other package to get their data or download shapefiles manually. Okay, so what I'm going to do is I'm going to say, I'm going to use the Tigris package, and I would like some urban areas. CB equals true gives me simplified boundaries. These are faster to download. I don't need a lot of precision here. If you're working with something like point data at a real low level, like super granular data, you don't use the simplified files. But if you're at the sky high view, use simplified ones, they download faster. SF file. Let's take a quick glimpse at these data. If I glimpse at my urbans data here, what I see is there are 3,601 urban areas with a whole bunch of information. I look over here though, and I see one thing very useful to me. Okay, I don't know what that is. I don't know what that is. This GeoID 10, I don't exactly recognize this somewhat, but you know what's useful to me? Name 10 says things like Colorado Springs, Colorado, South Bend, Indiana, what is Missouri? How did I forget my state codes? Anyway, yeah. So I don't know what any of this other junk is, but if I want to find things that are in Illinois, I know for sure it's going to have a capital IL in it. So what I'm going to do is I'm going to use my string manipulation functions. I'm going to say, take these urban areas and then filter them and find capital IL in the name. And I'm just taking a guess that no cities are named capital IL, that nobody has done a typo or something. There shouldn't be any reason to have a capital IL except for Illinois. Turns out I was right, but if worst case scenario, I could have did look at the end of the string or something. Okay. The other reason I did that is I actually didn't want it at the end of the string, because I also wanted to be able to do like IL -- Wisconsin or something and get urban boundaries that cross state lines. Okay, so now I got urban Illinois boundaries. So what I'm going to do is I'm going to take the exact same plot I just did, which was all of this and all of this, and I add another geom_sf call. I say geom_sf data equals urban Illinois, color equals black. We'll make an outline, black outline around it. No fill. I don't want to fill it in because I already have a fill from my census tracts. Size 0.1 makes a thin black line. Inherit AES false prevents it from inheriting things like the fill and the size from prior geometries. Just a nice thing to do. Okay, so the way geometries in R and ggplot work, whichever one you name like last goes on top. So it means that my filled in any black census tracts will be on the bottom and the urban boundaries will be on top. Okay, so let's see what it looks like. It looks kind of cool. So what we got here is we have this big, all of Illinois here, but tacked on top of it are the urban boundaries of all of the cities that are at least partially in Illinois. So for instance, this is the giant greater Chicago metro area over here, which extends into the bordering states. I don't know how I'm forgetting what city this is over here. I forget my cities. Anyway, major cities all over here, right? This is like Rockford over here and so on. My roommate's from Rockford. That's the only reason I know that. So yeah, urban boundaries, right? You can just layer additional things on here. Maybe you could also do things like put some point data on there, like the centroids of the cities. You could also then subtract the water from it, maybe add water to it. You could also add like major highways or something if you can get those shape files. Do whatever you want, right? You just got to get a shape file, layer it on. It's not hard to do. SF makes this stuff surprisingly easy. And I highly recommend recycling my code to do it. Just take it, use it, adapt it to your purposes. Okay, so that's what I got here. Does anybody have any questions about that? We have, solid 10 minutes here. Happy to, it doesn't even have to be specific to the lecture, anything geospatial or whatever. I'm happy to answer. While you're thinking about it though, you are now done with every required homework for this class. You're not required to do anything else because I don't assign things for like finals week because you got better things to worry about. But if you feel like it, there is an optional exercise. Homework 7 is an optional homework. You get a point for it if you want to do it, bonus extra credit, which is on mapping. It's about taking that restaurant inspection data and mapping the poisonous places to actual geographical locations. Hint, it's probably in a fraternity. So yeah, you can take a look at that. Anyway, that's what I got. Next week, we're going to go into tables and plots of model results, and then that'll be it for the class. So if you've got anything, let me know. Otherwise, get out of here.
Is there no lab on Monday since it's the holiday?
Oh yeah, no lab on Monday. And it also overlaps with the extra credit one, so it's kind of perfect. And usually like one person would show up anyway. So yeah, there'll be no lab on Monday.
Okay, thanks.
But if you do work on and you want help, Slack channel me, stuff like that.
Thank you.
Here's a good question. Do you happen to know when the 2020 ACS5 data will be available to query? I honestly have no idea. The census kind of got brutalized by the prior administration, and a lot of stuff have gotten gunked up, and they've also at the same time have migrated onto new back-end data systems. The combination of all of those has made the census stuff really unpredictable lately. I honestly have no idea when this stuff is going to be available. No. Thank you. Appreciate it. Yeah, this one's fun. Pure toys.